Hi everyone, welcome to this lesson on heat treatment. This has been quite difficult for some of you, this particular section, and I remember when I was learning it too when I was your age, I found it quite difficult to grasp the significance of it, but it's a really important and significant part of engineering. So I'd like to just go through it with you. So can you get your books, your Engineering Studies Workbook, the red one, go to page 48 and get your highlighter, and we'll go through it and I'll tell you fairly important areas of it for you to learn. I mean, you have to learn it all, but I'll try and make it as easy to remember as possible. So let's have a look at this diagram on page 48. This is the heat treatment of plain carbon steels that we're doing. We're not doing alloy steels. We're not doing non-ferrous metals. This is just for plain carbon steels. This diagram is a really important one because it shows you how heat treatment works. And so down here we have these grains. Now you show grains that have been work hardened by these little dashed lines there, but more importantly, you show them as elongated grains. And so this metal has been worked by forging, hammering, rolling, pressing. And when you deform a metal, you strain the bonds and you make it harder, less ductile, stronger, and sometimes it gets so hard that it becomes glass hard. And the place that I trained in, they had these huge machines and they were hammering away at these dies all the time. And after a couple of weeks, they got so work hardened that they became glass hard. And it was really important. And the engineer would work out, or the metallurgist would work out when to reheat treat those dies because they could shatter. And and this is an indication of what happens to the grains. And so as you look up here, these graphs here, you can see that the internal stress in a work-hardened metal here is quite high. And then as you heat it up, we're heating here, and there's a point where you have new grains forming, and that's called recrystallization. And these grains tend to form on the triple junctions where the grains meet. That's a triple junction. You've got one line there, one line there, one line there, and these new grains form at the expense of the old grains during the recrystallization temperature. And as you can see, the internal stress is getting less and less until you've got total recrystallization and you've relieved all of the internal stress. And these are the new grains that are forming, and they're basically equiax grains compared to these elongated grains here. These are the stress grains, and these are the unstressed grains. Now, if you hold it in the furnace for too long, you get over soaking, and you have to either work harden it or you have to reheat treat it. And this is a very costly process. And I remember the heat treater at this place where I used to train. He had the unfortunate problem that he put this really expensive die in the furnace and he turned the alarm on for a particular time, and it just happened that the lunch siren went at the same time as the alarm went on his furnace, and he didn't hear the alarm on the furnace. And about 2 hours later, we saw him running through the workshop, full speed, because these dies this is a long time ago, though. I think they were around about $10,000 each. And he got to the furnace and it was too late. They were over soaked. And so that meant that these dies couldn't go back into the machine straight away. And it required another couple of days' work on them. And it was unfortunate for him because he got the sack, because these were expensive dies. So let's just go back to these work hardened grains. So you can see here that they're stronger when they're work hardened, and they're harder. You can see the hardness here is quite high. But the ductility, the more work hardened they become, the less ductile they become. Remember, ductility is the ability of a material to be drawn into wire without fracturing. And so when it hits the recrystallization area, the ductility increases. And so make sure that you understand this, because this is a good indication of what happens when you recrystallize the grains. And so the first part is called recovery. So the work hardened elongated grains are stress relieved below the recrystallization temperature. So they're stress relieved, and then recrystallization, where you have new equiax grains form to replace the stressed old grains. And then you have grain growth. And as I said, you can't keep it in for extended periods of time because you'll get over soaking, and these grains are so large that the metal is quite weak. Okay, so that's an explanation of that diagram. I'd like to go over the different heat treatment processes. So the next one that we're going to have a look at is annealing. Now, put after this, it's softening. Annealing is softening the metal. And to soften plain carbon steels, you just heat it up to a particular temperature, which they call the transformation temperature. And I've just said that that's about red heat. And then you cool them as slowly as possible to get the softest possible state. And the main reasons for annealing is so that you relieve the internal stresses, you soften the metal so it can be further machined, and it produces a uniform grain structure. But full annealing is rarely done because it's quite expensive. The best way to do full annealing is to cool it really slowly, and a furnace cool is the slowest possible rate, and it costs a lot of money to cool and then reheat a furnace. So they don't generally do full annealing. Make sure that you can draw a full annealed macro structure of the grain. So these grains would be equiax, and these white grains here are ferrite. Ferrite is very ductile. And these grains here are perlite, and perlite is alternating grains of cementite and ferrite, and perlite forms wholly perlitic structure at 0.8%. And so at 0% carbon, you have total ferrite. So halfway between 0 and 0.8% is 0.4%. So you'll have 50% perlite and 50% ferrite. So this one here is 0.25% carbon. So you'll have 75% ferrite and 25% perlite. Okay, and this is just a bit on over soaking. Full annealing is not used as much as other softening processes because it's expensive, and the degree of softness is usually unnecessary. This is the first annealing process that we're going to do after full annealing. This is called process annealing. And process annealing is done on cold work metals that have a carbon content of less than 0.3%. The place that I used to work at, we had wire being fed into these bolt making machines, and the wire was drawn. It generally was around about, it went from say 13 millimeters diameter right up to 25, depending on the bolt size. And the wire came in coils and it was drawn, and so it was work hardened. And they had to soften it before it actually went into the heading dies in the bolt making machine. Otherwise, it would play havoc with the dies because the wire was work hardened and it was too hard and not ductile enough. And so before the wire was fed into the bolt making machine, they used to process anneal it. And it's they call it process annealing because I think it's done in the actual process before it goes into the machine. And they had two electrodes, 15,000 amp current going through into one part of the terminal through the wire, and it would heat it up. And then before it went into the machine, it would cool in air and it would process anneal it. It would soften it sufficiently so that it wouldn't play havoc with the dies. And so this is how the work hardened structure looks here. So this is the wire that has been drawn before it goes into the machine. And then after it's been processed, annealed, because it's called subcritical annealing, so you don't heat it up to red heat, you just heat it below red heat. The ferrite is made to be equiaxed during the process of annealing, but because the temperature isn't high enough, the pearlite is unaffected, so that still remains elongated like it is up here. But it's sufficiently soft enough because of the equiaxed ferrite, the recrystallized ferrite, so that it will not hinder the dies too much. And so that's called process annealing. And the important thing is that the metal is heated to below red heat, and it never ever gets to red heat for process annealing. So if you can highlight that and make sure that you know this here, ferrite is recrystallized to form equiaxed grains. There they are there, equiaxed grains, but the pearlite remains elongated. Another method of annealing is normalizing. Now, normalizing is heated, the steel is heated above red heat, where here it's below red heat. So can you highlight that? And it's called austenitizing. So above red heat, you know that the steel changes from body center cubic at room temperature to face center cubic because it forms austenite. And then it is cooled in still air to room temperature. And you can see these are quite large grains here, and you can see these are smaller grains. And the smaller grains, as you did when we did dislocations, if you've got more grain boundaries, it inhibits the movement of dislocation. So more grains means that the metal is less ductile and it is stronger and a little bit harder. Now, why do we have smaller grains here than that up here? Now, that's because the thermal gradient, as a result of heating it above red heat, is much higher, and so it will cool from a higher temperature, and so therefore it will cool quicker because of the higher initial temperature. And as you know, when you cool grains quickly and plain carbon steels, you have more nucleation points, so therefore the grains are smaller. Okay, so the higher temperature than process annealing means that the normalized metal cools faster due to the thermal gradient. In other words, this metal starts at a higher temperature, so therefore it'll cool quickly. It'll cool quicker than this here at a lower temperature, and that's the thermal gradient. It produces smaller grains than process annealing, which results in harder and stronger steel due to the finer grain structure. And make sure you know that the purpose of normalizing is to refine the grain structure, and that means make the grains more uniform and equal in size. And therefore, it allows uh, better machinability and if you have to machine it afterwards. So that's normalizing. Now, when you are dealing with carbon contents greater than 0.3%. Now, some books say 0.25, some even say 0.2. So it varies. And I'll just put 0.3 here because that's my experience. So if you want to soften plain carbon steels that have got carbon content greater than 0.3%, the idea is that you soak it for quite a while. Now, soaking means you get the outside temperature the same as the inside temperature. It doesn't melt it. It just makes sure that the furnace is at the right temperature for long enough so that the outside is the same temperature as the inside. And the idea with that is that you get the cementite, which is Fe3C, which is hard and brittle, to form in little spheroids as a result of the surface tension and the heat. And the steel then, after it's been soaked for sufficient length of time and given enough time for the cementite to form in these little spheroids, is then cooled slowly, fairly slowly. And I'm not sure that it's done in a furnace. I've seen it done outside a furnace, but you just say that it's been, the steel is then allowed to cool slowly. Now, the advantage of this is that when you go to machine this metal, when the tool actually is doing the cutting, if the cementite was in grains, the cementite is so hard that it starts to tear the metal when the tool cuts through it. But the idea with the spheroids is the spheroidal cementite is just pushed out of the way, and so it allows the metal to be machined, and it will give a much better surface finish. Okay, so that's spheroidized annealing. It's called subcritical annealing because it is heated to below red heat. So let's go on to hardening. Hardening is done by heating the steel with sufficient carbon. In other words, it's got to have greater than 0.3% carbon. Remember, if you've got 0.1% carbon, you can't harden it. And those steels are ideal to weld so that the heat of the weld, which can get to thousands of degrees with the arc, it doesn't cool quickly and form this substance, which we call martensite. So let's just go through what happens here. So we've got a piece of steel, and I used to do this with a mower blade when I was teaching full time. And I used to get these students in the workshop and I'd heat up a mower blade and heat it up to red heat. Then I'd quench it in water. Water is the most violent quenching medium. You can slow it up by using oil, or you can slow it up by using brine, which is salt water. but water is the quickest cooling medium, and sometimes you get quench cracking and you have to use oil to slow it up. But anyway, this is what happens here. So steel at room temperature is body center cubic. You heat it up to above the lower critical temperature, which is 723, and it forms austenite. And austenite is face center cubic. Now, if you allow it to cool slowly, it'll just go back to body center cubic. But if you quench it, it hasn't got enough time. The base center cubic structure hasn't got enough time to go back to body center cubic. And so it forms an interstitial phase, which is called martensite, and it's body-centered tetragonal. And the way to remember, looks like a toothpaste box, T for tetragonal, T for toothpaste. It's a strained structure, and it's very hard, very brittle. And with the mold blade, I used to heat it up, red heat, and then quench it, and then put it in a vise and just tap it with a hammer, and it would fracture because it was wholly martensitic, and it was good for nothing. You couldn't use it. It was so brittle. And so and this is the micrograph of martensite. There's a real micrograph, and this is a drawing of it. It's just like a bed of straw, and they call them acicular grains. And so when you're sketching, and I notice from some of the CWRs that have already been sent in, when you're actually labeling a diagram, make sure that your arrow doesn't end out here somewhere. Make sure that when you use a label, make sure that the arrow actually points to the grain. Don't just do an arrow like this out here. If you want to point to a martensite grain, you don't do that. You've got to actually point to the grain. And so when we have martensite forming, as I said, I used to actually throw it, get the kids standing on a bench, and I used to throw it on the ground, and they'd see how it would shatter. And once they've seen that, they realise how brittle it is. But I stopped doing that because one of the students hopped up on a desk and he didn't see the fan, and he got hit by the fan. So I had to stop doing that. But anyway, at least they remember the demonstration. So they saw the mold blade just fracture. I just had to tap it with a hammer and it would fracture. And so I used to get that same mold blade that was wholly martensitic, and I used to temper it. Now, tempering replaces brittleness with toughness. And the way that you temper it is you heat it up to a temperature well below the critical temperature, well below red heat, and then you allow it to cool in air. And the way the blacksmiths do it, they harden the metal, and then they just get a wire brush and bring up the shininess of the metal, and then they reheat it, and the oxide that's formed on the shiny part of the metal changes color with temperature. And these are called temper colors. And if you want to have a look at it, go to YouTube and just see what temper colors are. It's worthwhile doing that so that you remember it. And so the old blacksmiths never ever used to use a furnace to determine the temperature. And so when they used to temper hoes and shovels for the workers in the fields, they just used to shiny up the hardened steel and then just heat it up to a blue heat. Like the blue is around about 320 degrees, and then allow it to cool. Now, what happens then is when you temper it, you get the martensite, the acicular grains of martensite, having carbide come out of the solution, out of the grain, when you temper it, when you heat it up to below the lower critical temperature. And that allows the intense hardness and brittleness to be replaced with toughness. And so I used to heat the mold blade up to around about 330, I think, which is I think it was a blue from memory, and then allow it to cool and give the carbide time to diffuse out of the martensite. Then I'd put it in the vise and hammer it really hard, and you could see that it's gone from brittleness, massive brittleness, to toughness. And that's what tempering is. So it's important to remember that hardening and tempering is a really significant part of engineering. So heating the martensite at a lower temperature enables the carbon atoms that are trapped in the body center tetragonal martensite structure to diffuse out to form fine cementite, which is Fe3C. And make sure that you know that the microstructure, when you draw it, of tempered martensite is identical to the sketch of martensite that hasn't been tempered. And that's because this fine cementite that comes out with the reheating is submicroscopic, and you can't actually see it. So it's really important for you to be able to draw these. And as I said before, make sure that you label correctly, and make sure that some of the drawings that I've been receiving are pretty poor. So take a bit of care with your drawings and your labeling, and you'll reap the rewards. Okay, the last heat treatment process that I'm going to do is case or surface hardening. And there's situations like, for example, a car axle. Now, most of you know what a car axle is. It comes out from either the differential or the gearbox, which is attached to the differential for a front-wheel drive car. These are cylindrical, solid pieces of steel, and they have to not only be wear resistant on the outside, because you've got splines, and the splines create the drive, and it allows the suspension to move up and down. So they have to be hard to be wear resistant, but you don't want the axle to be brittle, because it takes high torque or high moment when it is accelerating. And so the ideal is to have an outer hard surface, which is called the case, and an inner low carbon tough material, which is called the core. And so you've got the best of both worlds: hard outer case and a soft, ductile, tough inner core. And there's basically two methods of doing this. The first method is for steels that do not have sufficient carbon in them. Remember that 0.2%. I've got 0.2% here because I'm varying between 0.3 and 0.2, but I don't mind if you use 0.3, as long as you know that steels below 0.2 or 0.3% carbon can't be hardened by heat treatment. They can only be hardened by work hardening. And so the idea with these steels that haven't got the required amount of carbon is to put the carbon in the case. And so they heat up the outer surface, or they heat the whole lot up. They put it into a high carbonaceous material, which they call hardite, I think. And they allow the carbon to diffuse through the outer layers. And the amount of time that it stays in the carbonaceous material will provide if the required depth of penetration. The longer, obviously, that it's in the carbonaceous material, the deeper the penetration of the carbon. So you've got an ideal setup so that you've got 0.8% carbon on the outside, which can be hardened, and you've got a core of around about 0.1 or 0.2% carbon on the inside. And so you're left with a tough core and a hard case. And so make sure that you know that carburizing is used on steels with less than about 0.2 or 0.3% carbon. Now, the other method, another method of case hardening steels less than 0.2 or 0.3% is nitriding. And so the idea is that you put it into a nitrogen-rich atmosphere. So the nitrogen will diffuse into the outer layers, and these will form hard nitride compounds in the case of the steel, and that's called nitriding. And an interesting thing, I don't know whether you've heard of the bone cutters of the 11th and 12th century. These were the swords that were the swords that you had to have in those days because, and the story goes that a blacksmith had a hot sword that he just forged, and he lent it up against the outside of the factory in the 11th century workshop, and his little boy, who had red hair, just happened to urinate on the sword, and he and the blacksmith saw this happen, and he did a few tests on the sword, and he found that it had remarkable properties. And so the ammonia from the urine put nitride compounds in the outer layers of the steel, and so you have these really efficient swords. And so anyway, all the blacksmiths of the day, this is how the story goes, were rounding up the red-headed boys to collect their urine so they could nitride. Of course, they didn't know it was nitriding their swords. And they eventually used donkey's urine one time that had been fed on a particular clover. And they said you didn't need to have red-headed little boy, you could use the donkeys. And of course, the urine was the same, was doing exactly the same thing. Okay, so that's called nitriding. Now, the second method that we're going to explain for case hardening is for steels that have greater than 0.3%, commonly from 0.4 to 0.6% carbon. Now, as you know, these can be hardened by heat treatment because they've got greater than 0.3% carbon in them. And so the idea is you just heat the outer layers up. You can use a flame to heat it up, and then you quench it quickly afterwards. So you don't allow the temperature to go deep into the core of the metal. And there's plenty of videos on this, how they heat it up. They can heat it up with oxyacetylene flame with large gear teeth. They have two oxyacetylene torches on either side of the gear tooth, and that goes along and heats up the surface layers of the gear tooth. And then you've got a water tap blasting the water out to cool it quickly so the temperature doesn't go too deep, so it doesn't heat up to a greater depth than what they wanted. The other way of doing it is by induction hardening, where they put a coil of metal around it. They do this with axles, and then they put a high current through it, and it induces the metal inside the coil to heat up, and so they keep the current going for the required amount of time to get the right depth of penetration of the heat, and then they quench it afterwards, and that's called flame and induction hardening. Okay, so that is ferrous metals, and now hardening and tempering non-ferrous metals is totally different, and we'll have a look at that next year. So I'll just stay on for anyone that wants to ask me any questions, but I'll speak to you next week. Bye.